Hello, everyone. So welcome to the first video for week 3 or our third full week, I guess like week 3.5, video 8. And so first, this is going to start with section 1.7. And so I'm lecturing from, again, on the yellow pad, but from the PDF notes for sections 1.7 and 1.8. So see attached PDF for the questions or the examples. And again, I'm going to use this yellow pad because there's a lot more I want to say here in terms of exposition than are in the actual notes. So I can flesh things out a bit more, give you some context, and then I'll work through the examples that are in the notes as well. Okay, so we're going to start with talking a little bit more about derivatives. And the good news is now that we've done all this kind of very hard technical work about derivative rules like power rule, sum rule, product rule, quotient rule, chain rule, all this hard stuff, and maybe a bit boring at times stuff, calculations, we now have the toolbox to be able to start doing some applications, to be able to understand the derivative in different contexts. And so that's what I want to get into now. We'll still need a little more practice with some mechanics in this video, but we'll start to broaden our understanding of the derivative bit this week than we have in the previous couple of weeks. So the good news is by the videos for the end of this week, we'll be doing a little bit more applications. And so hopefully it'll be a little more interesting. You might find it more interesting. Okay, so just recall, so what is the derivative? Let's just always recall this central idea of this section of the class. So we have y equals f of x, right? A function. So the derivative of y equals f of x is another function of y prime equals f prime of x, or we can write this as dd x f of x. And some people will also write this as dy dx. Okay, like it looks like a little quotient notation, and that's to encompass the idea, contain the idea that this is like a slope at a given point, a slope to the curve at a given point. So let me remind you that's what the meaning of the derivative actually is, right? So geometrically, the derivative is the function of slopes of f of x. That is to say that f prime of x is the slope, remember the slope of the tangent line to the graph of f at the point x f of x. So I've always drawn this kind of picture, but I can draw it again, and again, it's never bad to go through this again because this is kind of the central idea of this part of the class. So here's some function y equals f of x, and then you just pick some point, any point. So we can pick this point, say here. And this would be a point x f of x. You can blow the picture up a bit. And then if I draw, it's not the best tangent line, but there we go. That's pretty good. All right. Then the value f prime at x is the slope of the red line. I.e. tangent line. at x fx. Okay, so now I'm going to ask a question, and we kind of know the answer to this already from some of the discussion we had a few weeks ago when we first started talking about derivatives, but what's so special about the variable x? I mean, why are we always use this x? And the answer is that there's nothing special about it. We can take this derivative idea and compute derivatives for functions of any independent variable, right? And we saw this when we talked about the position versus time graph very early on in the class when I first introduced this idea of a tangent line. And we know that the slope of a tangent line to the position versus time graph gives you instantaneous speed of your car. And now in the language of derivatives, we can say the derivative of position function with respect to time variable is speed or velocity. So we can apply this notion to other functions of any independent variable. And then later in this week, we'll talk about like variables where x is the quantity of materials you produce at a company or a factory. And we can talk about a function as a variable, a function of population. You know, we can look at population growth and other applications for other variables. We don't have to use some abstract x all the time. The theory isn't married to that in any sense. So answer, nothing. We can define derivatives for any function of any independent variable, say t equals time, p equals population, capital T equals temperature, etc. In fact, and like what I was saying a minute ago, in fact, we already considered the position versus time function, the position versus time graph of a moving car back a couple of weeks ago. So if you remember, I was saying back then, it was this like thought experiment that we did. So we had t, s of t, so s of t was, was position of car after t hours. And we kind of reasoned that, say, if we were driving to New Orleans, we'd kind of start off, maybe get in the car, start the car slowly, get on the highway, hit some traffic, speed up again, and then eventually get to New Orleans. And say like, hopefully 2.5 hours. And what we reasoned then was the slope of the tangent line to the graph at a point, any point, say it's this point t, that the slope of that tangent line was exactly what your speedometer read in the car at that particular moment in time, right? That's what we did. Well, that's what we reasoned through back then. So in this case, right, the slope of tangent line to curve or to graph of s of t versus t is exactly instantaneous velocity, or what your speedometer, or what, if you want to think of it this way, I mean, there's a slight difference between velocity and speed I won't get into right now. I'll save that for physics, but for all intents and purposes, you can think of it in this example, or what your speedometer is reading that's just kind of a speed. So it's what your speedometer is reading at that time. Okay, now we have, at the time we talked about this, we were just talking about slopes of lines. We didn't have the language of derivatives. We didn't know how to compute derivatives. But now we know all that jazz, right? So now we can say that, the derivative of the position function with respect to time is velocity. S prime of t, which is sometimes written as ds dt, is the velocity of the car. And so we can actually write, so using physics kind of notation, so we would say v of t, or the velocity of the car, is s prime of t equals ds dt. So the function of slopes to the position, to the position versus time graph is, that function of slopes is the velocity function. It is exactly what the speedometer is saying in this example as you drive to New Orleans. Okay, so we've seen this idea of taking derivatives with respect to different independent variables. We can think of, here we have time as a variable rather than some abstract x. Now this example is nice because it illustrates what you can keep doing with derivatives. So we took the derivative of the position, we got the velocity, right? Now we have that, so velocity is another function, right? So at any point t, right? So you can think of this v of t as a new function. So note, right? V of t is a new function, right? So v of t is speed of car at time t. So you just input the t, and it gives you the speed, the reading of the speedometer, right? Now, so we have a function, we can start again. We have this function, we can take the velocity function and we can differentiate it, right? And we can, if we're doing the right thing, this should have some meaning, some important meaning, and it does. So since v of t is a function, we can differentiate it. So we can consider v prime of t equals dv dt. And this would be the slope to v of t versus t graph. Let me clean that up a bit. At an arbitrary time t. Now, it depends on your physics background about what, maybe the meaning of this may not be super obvious unless you've done a decent amount of physics, but let's think through it using the idea also that the derivative is a rate of change, which we've talked about and we will explore more this coming week. So recall also, right, that the derivative gives us the instantaneous rate of change of v as a function of t at an arbitrary point. All right? So if we think of it that way, and we saw this position a couple weeks ago, the rate of change of position is just the velocity, it's just the speed. And that's why we had the slope of the tangent line being the speed of the car. If you do the same thing with velocity, what's the rate of change of velocity, right? So think intuitively. So the rate of change of velocity would mean how you're speeding up or maybe slowing down, right? So you're speeding up really, really fast, you'd expect a high, very steep positive slope of the v of t graph, and this v of t function would be a very large positive value, right? V prime of t function. Or if you're coming to a stop, you'd expect that you're slowing down, so the velocity is actually decreasing. So you'd expect this to have some negative value. But if that rate of change of velocity that measures the quantity that's measuring how you're speeding up and how you're slowing down, like the magnitude of how much you're speeding up or slowing down, in physics, that's acceleration. So the rate of change of velocity with respect to time is, in physics, what we call the acceleration of the object, that you're observing. So, and is denoted by A of t. And now, so what did we just say? So the acceleration then is the derivative of a velocity, which we write as v prime or dv dt in this other notation. Right? Now, it's very important in these kind of, you're working with these things, to remember like the chain of derivatives. Like what, we started with, what did we start with? We started with position. We took the derivative of position, we got velocity. We took the derivative of velocity, we got acceleration. But we should remember that acceleration function came from taking the position function and differentiating it twice. Because this sequence of taking rates of change is very, very important in applications and trying to solve problems involving rates of change, as we'll see later on. So, but v of t was the derivative of position, right? So we say, so we see, because we're seeing it right now, it's present tense, that we obtain acceleration of the car by differentiating the position function twice. We differentiated twice. So in other words, so we say as that acceleration S of t, A of t, sorry, is the second derivative of position. And we write that A of t is S double prime of t, or is d squared dt squared S of t in the other notation. And so it's a very important kind of thing to remember. I'll state the general case in a second. But I should just say we can keep going. I mean, why stop here, right? We can, so A of t is this acceleration is a function of time. So we can differentiate it again. It's with respect to time. So you'd have A prime of t, and this would be the third derivative of position, right? Because you've taken, to get to this A prime of t, right? You've taken the position function and differentiated 3 times in succession. And that's written like this, which is kind of awkward. So t cubed dt cubed S of t. And physically, this is also important. So this is called the jerk. And the reason it's called the jerk comes from Newton's second law. I don't want to go too much into the physics, but if you have done some physics, force is sorry, acceleration is proportional to force. So F force is mass times acceleration. F equals m times a. And so the derivative of acceleration tells you something about the derivative of the force on the object, how the force is changing. And so that's thought of as the jerk on the object out of the car in this case. Okay, so, and after you could, and again, you could keep going, but after you get beyond the second, and really in many cases after the second, but certainly for our purposes after the third derivative, you don't get quantities that you might be super useful for understanding the graph or applications. So, so I should say from this examples of this type of thing of taking a function and constructing these higher derivatives, second, third derivative, this can be done in any abstract setting, again, with our friend, the variable x. So let me just review that in just a quick moment. Okay, so let's talk about general higher derivatives. Given an arbitrary function, y equals f of x, we can construct its first, second, and third derivatives. Much as we did for the position example. So there's a table in the notes, and let me kind of try to reproduce that here. I'll do something a little bit different, but well, I'll do more or less the same thing, but I might use a slightly different terminology for some things. But so notation, function, first deriv. So I won't write derivative, second, and then the third one. So there's a so-called prime notation. This was developed by Newton. So elsewhere you might hear this called Newton's notation. And then there's this DDX notation, which we've been also using. This is called Leibniz notation. So calculus was developed simultaneously by two different people, Newton and Leibniz, and they were writing to each other. Historians kind of debate if maybe one stole the ideas from the other, but no one's really made sense of that. But anyways, we can just we won't have to get involved in that debate. But it's, you know, if you're interested about it, it's kind of an interesting story. You can read about it. Okay, so in a Newton's notation, you write your arbitrary function as f at x. Your first derivative is f prime at x. So that's the derivative of f, the slope of the tangent lines to f. Your second derivative is f double prime at x, 2 primes. That's the slope of the tangent lines to f prime, the derivative of this guy. And then you can do the third one, you have 3 primes. And so that would be the slope of the functions of slopes of the tangent lines to f double prime. So and I'll do the little physics example again, so you see what what we can summarize what we did in those examples. But for general functions, what these mean in terms of f, right, has to do with what f is measuring. And so there's no general statement for what these things actually mean conceptually. And we'll see in examples what they mean and how you interpret them. So in this case, in the Leibniz notation, right, you have the function is denoted by y. And so the first derivative is dy dx. The second is d squared y dx squared. And the third is d cubed y dx cubed. d cubed y dx cubed. Okay, and so, and I should just say here, I'll add, oh, sorry, the Leibniz got below where it's supposed to go. Oh, the Leibniz spelled that way. So this last column will do this physicsy stuff. So this is physics. So position function. So now variable is t instead of x, so position. The first derivative, and I like for the physics to do either notation, but because I see. Well, sorry, I said for the physics, I like to kind of, you can do whatever you want, but I like the Leibniz notation because it tells you what the units are. So if you think of position as like miles, you know, s is being in miles per t hours, then from the Leibniz you see miles per hour as a rate of change of position with respect to time in hours, but it's awkward to write sometimes. So then you could also have the second derivative of position, right? And then that's, of course, this guy. And the third derivative of position. Oh, sorry, clean that up. And the meaning of this is, well, position, velocity, and this is acceleration, and this is jerk. So those are like, you know, so the first two rows of this table, we have this abstract mumbo jumbo that you can do for any function. And the second two rows is kind of a different table. It's a physics table in some sense. And it gives you some concrete ideas of what these things mean in one particular example. So something to kind of visualize, keep in your head as to what these actually mean in an example. Okay. So I should just say there's, like I said, I like the Leibniz notation in the physics case because it tells me something about units, but there is a danger for kind of understanding it. So I want to just mention that. So danger with Leibniz notation. Okay, so what's the danger? So there's a bunch of dangers. So dy dx, which is the derivative of y with respect to x, is not, oh, sorry, messy, is not the quotient of quantity dy by quantity dx. Okay, so you cannot treat this as a quotient of dy by dx. So that's, I mean, intuitively, it's a slope. So you think of it as like rise over run instantaneously. That's what the little d's are for. But you cannot manipulate it like you would a fraction a over b, right? So you have to kind of remember that this is like a standard notation to conceptualize a slope, but it's not really dy divided by dx. Okay, so like don't do things like, for now, dy dx times dx equals dy. Okay, no. Okay, the other thing, and this is an issue with the higher derivatives. Sometimes people call these higher order derivatives. I would be, so you have d squared dy dx squared. This is not equal to, don't think of this as dy dx squared. And this is very confusing as a student, I think. I mean, it was kind of confusing for me when I first saw this, of why this notation here has this squares in it when it's not really what we think is a square. So I should explain. So the notation d squared dy dx squared comes from applying the operation of differentiation d dx to the function y equals, say, y as a function of x twice. So that's how to think about it. So you start with y, you apply this differentiation operation to produce your new function, dy dx, the derivative function. Then you apply that operation again to produce the derivative of the derivative, or the second derivative of y. And when you apply this again, so you think of d dx applied to dy dx being d squared y dx squared. So that's where it comes from. That's where that notation comes from. You think of it as applying the operation of differentiation twice. You think of the operation as differentiation as being encoded as d dx, this kind of take the derivative with respect to x operator. And so that's and for the third derivative, you'd go one more time if you like. So if we want to do the third, you would take, dy, the second derivative, you apply d dx, and you get this. Okay, so I took almost half an hour to explain what's in the first two lines of the notes and to give you some context for that, but I wanted to do that. So I'm going to skip the example where you differentiate this p functions. Hopefully now you get a sense that whatever independent variable you use, it doesn't matter. Derivative is the same thing. Same rules apply. But I want to do the examples where we have to deal with the higher derivatives and all this other jazz in the bottom of page 1 of the notes and page 2. And then I'll stop as we get to how to use the derivative in applications, and we'll save that for the next video. Okay, so finally, examples. So we've thought of the pitfalls, we've seen some context for what these things are, and now we can move on. So it needs a new crisp page here, virtual page. Okay, so find and evaluate the first, second, and third derivatives at a given point. So 1. So for f of x, we're going to stick with an abstract example first, is x cubed plus 2x minus 11 at x equals 1. And I'm just going to I'll use the Newton notation. I mean, maybe in the next one, we'll use Leibniz notation. So we can get a feel of Leibniz notation. But for now, we'll just use this prime and Newton notation. So the first derivative from the sum and power rules, right? You get derivative x cubed is 3x squared, derivative of 2x is plus 2, and the derivative of minus 11, minus 11 is a constant, is 0. So that's the first derivative. Now we evaluate it at at 1, thankfully, not 11. So f prime at 1 equals 3 times 1 squared plus 2 is 5. The second derivative, we differentiate now this guy. We get 6x, right, from the constant multiple and power rule, and the derivative of 2 is 0. So the evaluation at 1 is nice, it's just 6. And I guess we want to do a third just for fun. So the third one is super easy, right? Derivative of 6x. 6x is a line of slope 6. If you want to go back to basics, so you just use the sum and power rule again. The constant multiple and power rule. Derivative is 6. So that's a constant function 6. So for all x, the slope of this function, the second derivative is 6. So f triple prime evaluated at 1 is 6. So that was kind of anticlimactic, maybe. So make sure you're kind of cool with that. Okay, so a second example. So for the second example, okay, we start with this function, which is a function of, there's a whole bunch of crap in here. So we have capital T x cubed plus 3x capital P plus capital T to the 5. We want to find the derivatives, the first, second, third derivatives with respect to the variable capital T at capital T equals -1. Okay, so now when you're doing this, mentally, this is a bit of a challenge. So you have to think of the x, anything involving the x and the capital P, as you have to treat that as you would treat a constant. So this is an important bit of distinction. So even though we know what derivatives mean, implementing it in a situation like this is not something we've done. So to do this, we have to think of any expression of x or p as a constant, because these things do not depend on t. As far as capital T is concerned, these expressions are constant. So let me take you through how to do this slowly. So I'll use the Leibniz notation. So d capital T will be d dt tx cubed plus 3xp plus t to the 5th. Okay, so go back to basics. We use the sum rule. So the derivative with respect to capital T of the quantity tx cubed plus the derivative with respect to capital T of 3x to the p plus the derivative with respect to capital T of t to the 5th. Now, as far as capital T is concerned, x cubed is a constant. This entire expression is a constant. And then this just only involves capital T. So we know how to handle the last one. So to the first one, x cubed is a constant. So by constant multiple rule, we can pull out the x cubed from that expression. Now, this whole thing is a constant. It does not, as far as capital T is concerned, it does not depend upon t at all.